right, wonderful. Good morning. My name is Keira Powers, and this summer I assessed the cooling efficiency of an NMR and DNP system using methanol as an NMR thermometer. So pictured here in figure 1 is the system in question. In purple, we have the magnet itself. In orange, we have the gyrotron, which generates the microwaves that we use in DNP that shoots up into the sample. And in the blue, we have the cooling system, which inputs cooled nitrogen gas at whatever temperature we set it to up into the sample chamber. This microwave that comes with DNP is great because it increases the sensitivity of NMR, but it also causes polar molecules to heat. And if the molecule is heated too much, then we'll get no signal from the sample. So the issue that's requiring us to use an NMR thermometer comes from the position of the sample and the thermometer already in the system. So here we have the sample inside the sample chamber, and that is where the microwave heating occurs. Once the microwave hits the sample, we have heating localized at that point. But the thermometer is far below it in the nitrogen gas tube. So the only temperature that we can pick up currently is from the nitrogen gas that we're inputting into the sample chamber. So in order to get a temperature reading at the sample itself, we're going to use methanol as an NMR thermometer. This was from a previous study, and we're reproducing it on our own system to assess its cooling capabilities. For proton NMR, we have two signals. We have the methyl signal pictured in pink in both figure 2 and figure 3 from the 3 equivalent methyl hydrogens, and then one from the hydroxyl signal. And this study has shown us that with the varying temperature, we also see a varying distance between these peaks in NMR spectra. So when we go from -10 Celsius to -70 Celsius, for example, we can see that the distance between these peaks lengthens from 1.7 ppm to 2.15. So we assessed our system from about room temperature to -80. That's the range that we put our nitrogen gas to. And from each of those NMR spectra, we took the distance between the peaks, plugged them in to the polynomial equation developed previously to output the actual temperature inside the sample chamber. And what we found was that the set temperature of the nitrogen gas does indeed vary significantly from the resulting temperature of the sample. However, this isn't an issue for typical NMR because we can keep the sample at about -63 Celsius, which is plenty efficient enough to keep it below freezing point for NMR measurements. However, our next steps would be to apply this to DNP, to activate the microwave, see that localized heating, and determine if we can keep the sample at room temperature for these measurements and therefore maintain a good quality signal. Thank you.